Okay, assalamu alaikum ikhwan. Hope everything's going well. I'm just gonna quickly fly through chapter 14. I don't think this is gonna take much time, to be honest. I'm gonna do up until, so it's 19 questions. Yeah, 19 questions, okay. I'm not gonna do, what am I not gonna do? Some questions I'm not gonna do, because I don't know how to. But, yeah, like this, for example. Or actually, I'll have a look at it. But, let's start. So this chapter is mainly just ICE table, but there's a shortcut to basically half of the questions in this that allows you to solve it much faster, and I think that's why we're going to go through this a lot quicker. So let's go. Identify the conjugate acid-base pairs in the following reaction. So acids, we know they have H, and we know, well, like the general rule of thumb is that acids have H, or acids are proton donors, and bases have OH, and they're proton acceptors, right? Let me just double check that reading. I'm going to be sending these notes, so don't worry. Am I recording? Yes, I am. Okay. Okay, sorry, my dad walked in. But yes, so there's two definitions. According to the Arrhenius definition, I don't know how to say his name. Arrhenius, whatever. The Arrhenius definition of acids and bases. Acids H plus, bases OH. According to the Bronsted-Lowry definition, acids are proton donors and bases are proton acceptors. So let's have a look at this question here. All right. Um, so we have NH3. This is our base in this case. We can see NH4 it became NH4 plus, right? So it accepted a proton. So we know bases are proton acceptors, acids are proton donors. So in this case, NH3 is the base, right? Therefore, NH4 is going to be the conjugate acid. It's like conjugate and then opposite of what NH3 is. NH3 is a base, therefore NH4 is an acid, so conjugate acid. Okay. H2O in this case becomes OH minus since it gave off an electron. So it gave off a proton. And we know acids are proton donors. So we could say in this case H2O is an acid and OH minus is the conjugate base. Let's have a look at this question. So HC3H5OH becomes C3H5OH minus. So it gave off an electron. Sorry, it gave off a proton, this one here, right? So it gave off a proton. It is a proton donor. Yeah, so acids are proton donors. Therefore, this is our acid, and this is our conjugate base. Therefore, and let's have a look at this, right? H2O becomes H3O. We know bases are proton acceptors, so H2O is our base, H3O is our conjugate acid. And yeah, this is just the answer, but I already know it's correct, so same thing applies here. This, it had a positive charge, then it became, then that went away because it gave off a proton. Therefore, this is an acid. Okay, yeah, this is an acid, and this is its conjugate base. Here, H2O accepted an electron, sorry, accepted a proton, so accepted an H atom. So this was our base, and this is our conjugate acid. So acid, conjugate base, base, conjugate acid. Acid strength. Explain why water becomes a better electrolyte at higher temperature. At higher temperatures, the water dissociates into. Let me just. I'm gonna read out the definition for you because I don't want to say something and have it be wrong. So yeah, dissociation of water is an endothermic process. So increasing the temperature favors endothermic reactions, which in turn allows for an increased concentration of H plus atoms, right? And H plus atoms, when there's a higher amount of H plus atoms, it allows it to be a better electrolyte. Let's just read their definition. Dissociation of water is an endothermic process. Increasing the temperature favors endothermic reactions. Therefore, at a higher temperature, more water molecules dissociate, producing more protons and increasing H+. As a result, Kw increases in value, and water becomes a better electrolyte and a stronger acid at a higher temperature. Okay. 3. Calculate the concentration of H plus and OH minus of water at temperature where Kw is that. So, we know that Kw is the Kw relation is Kw equals to concentration of OH minus times H plus. They gave us Kw here to be this, so you just do radical 4.0 times 10 power negative 14. And it is 2 times 10 power negative 7. Okay, next. Calculate the OH minus concentration. So calculate the H plus and the OH minus concentration of a 0.2 molar HCl acid solution. HCl aqueous solution. Right, so we know that HCl is a strong acid, right? You're going to memorize that. So it dissociates completely. Therefore, the concentration of H ions is 0.2 molar. So, this is 0.2 molar. Now, we can use the Kw relation, which is concentration of H plus times the concentration of OH minus, right? When they don't give you a value for Kw, Kw is just 1.0 times 10 to the power of negative 14. So, we do that and we solve for OH. So, pull out the calculator. 1.0 times 10 power negative 14 divided by, so 0.20. 5 times 10 power negative 14. Yeah, okay. Next. Find the OH concentration and OH minus concentration in a solution of pH where the pH is 3.00. So we know the formula for pH to be pH is equal to negative log H plus concentration. And for pOH, it's equal to negative log concentration of OH minus ions. Therefore, we can just solve for this. You can solve for it on the calculator, shift solve. But I also believe there's a formula for this if you don't have shift solve on your calculator. I just don't know it. So here, pH is 3, so 3.0 equals to negative log x. This is going to give us our H concentration. So concentration of H plus is equal to 1 times 10 power negative 3. Now we apply the Kw relation. So Kw, and then you know the rest. I'm not going to type it out, so I don't want to waste time. When we divide 1.0 times 10 power negative 14, sorry, with 1.0 times 10 power negative 3, we get 1.0 times 10 to the power of negative 11. Let me just double check. Yeah, okay. Now, part B. So, let me just erase this. POH is equal to negative log OH. So, calculator, here they give us POH to be 10, so 10 equals to negative log x. So for x, concentration of OH minus in this case, what was it? 1.0 times 10 power negative 10. So 1.0 times 10 to the power negative 10. Therefore, H plus is, if we apply the Kw relation, which is Kw equals to H plus times OH minus, and we solve for H plus because we have K, which is 1.0 times 10 to the power of negative 14, and OH, which is this, you get H to be 1.0 times 10 to the power of negative 4. these questions, if you get them in written part, you're gonna have to do ICE. I'm gonna do ICE table for one of these questions, and the rest I'm gonna use the shortcut. So HNO2, I'm gonna apply ICE for the solution for this question. HNO2 is a weak acid with dissociation constant of Ka equals to that. Calculate the pH. So uh, so let's just write down the reaction. HNO2, I believe, is with water. Oh no, just dissociation. Okay, to give H plus and NO2 minus. So we know H plus initially, so ICE. So initially it's 0.3. We don't have initial concentrations for these two, and then they change. So minus x plus x plus x, and then 0.3 minus x. As you said, as I said in the previous recording, you get this by just combining these two. So 0.3 minus x, and here nothing plus x, so just x, and then nothing plus x, so just x, and then you write down the Ka expression. So that's going to be Ka is equal to product over reactants, so concentration of H plus times the concentration of OH minus over, sorry, not OH minus, my bad, NO2 minus over concentration of H and O2. So we can just substitute all these in and equate it to this. Hello. This here is a very small number. Wait, I'm just going to read the IC table. So the result here is a very small number. Therefore, 0.30 minus x, we can assume that x is a very small number, since our result here is a very small number. Therefore, we can just rewrite it as 0.30, and that's it. So x times x, so x squared over 0.30 gives this. And I'm going to prove to you that this is a very small number later on. I'm just going to solve it on the calculator now. So x squared over 0.30 minus, no, sorry, just 0.30 equals to 5.0 times 10 to the power negative 5. And we got the concentration of, no, so we got x to be 3 point, okay, so three significant figures, 3.87. 3.87 times 10 to the power of negative 3, right? So if we were to do 0.30 minus 3.87 times 10 to the power of negative 3, we're still going to get approximately 0.30, so it doesn't really matter, right? And I'm going to solve it on the calculator with this, with x, with 0.30 minus x, so x squared over 0.30 minus x equals to 5.0 times 10 to the power negative 5. And we got 3.84, so it's not that big of a difference. Now we know x is this, we can substitute it into, well, we can substitute it into, so this was H plus and this was NO2 minus. We can substitute x into here, so the concentration of x is equal, so H, sorry, is equal to 3.87 times 10 to the power of negative 3. Now we can apply the pH formula, so negative log this, and we're going to get our answer. After this, I'm going to show you the shortcut, and I'm going to apply it to the rest of the formulas for the rest of the questions. There's one question though where you can't apply the formula because the acid in mind is a strong acid, and you can't apply the formula I'm about to show you for strong acids. So, negative log 3.87 times 10 power negative 3, yeah, okay, equal to 2.41. Their answer, 2.4. Hello. Now, uh, here, number 7. I'm going to show you so what I just did, you do in case you get these types of questions in written parts, right? For the computer correctable parts, if they give you a weak acid, and to find the concentration of the the, the H, right? You do radical Ka times the concentration. This is for acids. And for bases, you do radical Kb times concentration. This is going to give you the concentration of OH minus. This is going to give you the concentration of H plus. So I believe anyway. Or honestly, no, it's going to give you the concentration of all the species, which is just going to be that. So yeah. Here is a radical KAC for number 7. Radical, so Ka is 5.00 times 10 power negative 5 times the concentration, which is 2 molar, and we got 0.01. Yeah, so we got H, oh, so they wanted, this is number 7, right? Okay, yeah. So we got H and NO2 minus to be 0.01, and then for HNO2, you're just going to do the answer, so 0.01. So the initial concentration, 2.00 minus 0.001, and the answer you got from doing radical KAC, and you're going to get 1.99. Now, number 8, same thing. You know, here they want us to find percentage dissociation. So we're just going to do same thing. Radical KAC. Here they give us the same values of A and concentration. So the amount associated is 0.01 molar, right? And initially we had, and versus the total amount of the total concentration, which is 2 molar times 100 because percent, right? So 0, 0.01 divided by 2.0 times 100, 0.5%, and yeah, 0.5%. In the written part, you would apply this formula. It's going to be in the notes that I'm going to send, where alpha is just oh, here you're solving for alpha. Yeah. So alpha is going to be the concentration. Yeah. Am I right about that? Wait. No, wait. What is alpha? I never got what alpha meant, but you can just apply this formula and yeah, I don't use this. Yeah, here they told us alpha, or you can use this formula. So this is the one I use. So the concentration of H plus over the concentration of HNO2, and we got the percent association to be 0.05, 0.5 rather. Or you can do ICE table, which is what you should do for written parts. Actually, I think you can apply all these. You just can't apply radical KAC. Yeah. Okay. Number 9. Okay, 20 minutes, good. HCN is a very weak acid, as it's only this much dissociated in that concentration. Calculate the value of the dissociation constant of HCN. So we know the dissociation. So dissociation is equal to concentration that dissociated over the concentration itself. So 1.0 in this case. So they told us, and obviously times 100. So here 5.0 times 10 to the power of negative 3. Let me just double check my solving so I don't give you guys something wrong. I think this is correct what I'm doing either way. I'm just going to carry on with it and see if it's wrong. If it's wrong, I'm going to do what they taught you, what they did. Okay, yeah, so, yeah, okay, I was wrong. How far off are we? Okay, we're very far off. Um, so, percent dissociation, we're going to apply this formula, which is Ka is equal to alpha squared times the concentration over 1 minus alpha, where alpha in this case is, so they said alpha is that. Right, okay. So, alpha is the amount dissociated. Okay, here they told us it's 5.0 times 10 to the power negative 3%. So here we just divide by 100 to remove the percent, so it's times 10 to the power negative 5. Then we apply the formula Ka is equal to, what was it, alpha squared C over 1 minus alpha? Yeah, alpha squared C 1 minus alpha. So, go to the calculator. Yeah, in this case, the value of dissociation, so dissociation constant is just Ka, because this is an acid, right? So we're solving for Ka. So if you want to know when to apply this formula, just look if they gave you Ka in the question, I suppose. So Ka is equal to equal to alpha squared, so 5.0 times 10 power negative 5 squared times the concentration, which is 1.0, right? Yeah, over 1 minus 5.0 times 10 power negative 3. We got Ka to be 2.5 to two significant figures, or 3, whatever. 2.51 times 10 power negative 9. And in this case, they took two significant figures, so 2.5 times 10 to the power 2.5 times 10 to the power negative 9. 2.5 times 10 to the power negative 9 over here. Nice, okay. Number 10. Find the H plus, OH minus, pH and OH and pH and POH of a 0.2 molar NaOH aqueous solution. Just give me a sec, guys. Okay. NaOH is a strong base, so we know that it completely dissociates. So in this case, to find the concentration of OH minus, it's just going to be 0.2, because NaOH is a strong base that totally dissociates. So this is 0.2. Now we apply the Kw relation to find the OH, to find the H plus concentration. So 1.0 times 10 to the power negative 14 equals to concentration of H times concentration of OH, which is 5 times 10 to the power negative 14. So now to find the pH, you just do negative log this. To find POH, you do negative log this. So this is 13.3, was it? Yeah, 13.3. And this was, so let's do it. Negative log 0.2 is 0.69. Nice. So it is 0.7. Here it's two significant figures, so yeah, 0.7. 0.70. Was it 0.7? Yeah, 0.70. I feel like something is wrong with this. I don't know. Yeah, okay, 0.7 and 13.30. Or 13 because here two significant figures. But they did a different method of finding POH. Instead of just finding the concentration of OH, they did pH was equal to 14, and then they subtracted. So pH. So wait, this is formula where pH plus POH is equal to 14, and they just solved for this. They solved for POH, which is 13.3. Okay, next. Find the percent association of a 2 molar NH3 solution. We know NH3 is a weak base, and we can also tell that it's a weak base judging by the dissociation constant. It's a very small number, right? 10 to the power negative 5. So, radical Kb times concentration. So 1.8. So I'm gonna type it into the calculator, so don't waste time. So it's like 1.8 times 10 to the power negative 5 times 2.0. So we got the amount dissociated, 6 times 10 to the power negative 3. Now we put it over 2, which is the concentration, 2.0 times 100. So divided by 2 times 100. And we got 0.3% or 0.30, whatever. 0.3%. Again, in written, you're going to have to do the ICE table with the same assumption where you remove this because it's a very small number, our KB. Oh, what question did we just do? We did 11, okay. Okay, now I'm going to do 14 alone because 14 requires you to do ICE table. So the pH of a 5 molar NH3 concentration is 12. Find the association constant Kb of NH3. Okay. Here they give us the pH of a base. So to find POH, what are they asking for here? They're asking for Kb. Let me try something, and if it works, then I'll do it. I'm still solving, so okay. Okay, I did something wrong. What they do here, they just did ICE table to find the concentration of the OH minus. Yeah, okay, so my method is wrong. Let me just solve it the normal way. So ICE table, the dissociation, so NH3 plus H2O gives off NH4 plus and OH minus. So NH3 initially is 5 molar, so 5. H2O liquid, nothing, we don't consider it. NH4 plus we don't know, so it's not there. And OH minus we don't know. Then they change. This is minus X, plus X, and plus X. So 5 minus X, X, and X. Now let's write down the expression. So product over reactants, so X times X over 5 minus X. But here NH3 is a weak base, so we can remove the minus X, it's just going to be 5 equals to KB. Now, how are we going to find X so we can find KB, right? We can find X from here, what they told us. So they told us that the pH is equal to 12, right? So we could do what they did in the previous question, which was pH plus POH equals to 14, and then you would solve for POH. So when you do that, you get POH is equal to 12, right? And then you do negative log the concentration of OH minus equals to 12. No, wait, oh my god, I'm so bad at math, it hurts. This is 2. This is 2, you guys. This is 2. This is 12. This is 2. 2 plus 12, 14. Okay. So 2 is equal to negative log OH minus. You can solve for OH minus. And we got OH minus concentration to be 0.01. Therefore, X is equal to 0.01 because this is the OH minus concentration at equilibrium, and this here represents OH minus concentration at equilibrium, so 0.01. Then, now that we have the value of X, we can do 0.01. So X times X is X squared, so 0.01 times 0.01 is 0.01 squared over 5. Solve and you'll get KB. And I got 2 times 10 power negative 5 as a dissociation constant, and I got 2 times 10 power negative 5. Hello. Okay, 13. What is this? Okay, so find the pH of a 2 molar concentration. Sorry, find the pH of a 2 molar NH3 solution given Kb is that. So this is, we can just apply radical KBC. So 1.8 times 10 power negative 5. 1.8 times 10 negative 5 times 2. We got the concentration of H to be 6 times 10 power negative 3, so huh? Oh my god, I'm so, wait, how did I miss out on that? No, you guys, they asked for pH, okay? They asked for pH here. So this concentration that we got is So wait, let me do this on my calculator and then I'll huh. Right, okay. So this 6 times 10 power negative 3, that's the concentration of the base after it's when at equilibrium. So this is going to be of the base, right? Base, keep that in mind since energy 3 is a base. So 6 times 10 power negative 3. So when you do negative log 6 times 10 power negative 3, let me sneeze. Alhamdulillah. Okay, so you get POH, or POH is 2.2. You want to find pH, so you do 14 minus 2.2. 14 minus 2.2 is 11.8. Okay, let me just have a look at the rest of the answers. The questions are, okay, 15, I probably won't do. 15, I don't know how to do. 16, I don't. 17, I don't. 18, top, I'll skip that. I'll just do the past papers. 19, I'll do. If I figure out how to do those questions later, which I probably will, I'm going to record and solve those questions. So, 14. Now, H2SO4 is a strong acid. We can tell by the Ka. It's not that small of a number compared to the other Kas we've seen. So here we have to do ICE table since we can't just do radical KAC. So, uh, H2SO4. Let me just, I think I have the reaction memorized. I just don't, I want to double check it. So H2SO4. Yeah, okay. Okay. So H2SO4. What are they doing here? What is this? What are they doing here? Yeah, no. What is this? I'm confused. Because I think I have an idea of what to do, but they're doing something else. Okay. So, wait, in that case, just give me a sec, guys, yeah? Oh, okay, that makes sense. They gave us the Ka of HSO4 minus, not H2SO4. And HSO4 minus is a weak acid, actually. So I think we can just apply radical KAC right here. No, wait, we can't. Yeah, no, we can't. Okay. So here, they give us the Ka of HSO4 minus. We know the H2SO4 dissociates into H plus and HSO4 minus. Now, we're going to do the ICE table for this one. So HSO4 minus gives H plus and SO4 2 minus. So, we know that H2SO4 is a strong acid, therefore the concentration at equilibrium here is 0.2 molar, and this is also 0.2 molar. So we can say that initially this concentration was 0.2. This we don't know, this we don't know. Minus x plus x plus x combine. So 0.2 minus x, nothing plus x is x, and nothing plus x is x. And now you could solve for Ka. So you write down the expression. Wait, so ignore what I said about this, because about this being a weak. No, HSO4 is a weak acid. Let me just double check. It's a weak acid. Wait. Yeah, okay, so it's a weak acid because. So ignore what I said about this earlier, where it's a strong acid because the dissociation constant wasn't as small compared as the other ones. But yeah. So now we can apply KAC, so product over reactants. So this times this over this. So x times x over this. So x times x is just x squared over 0.2 minus x. Now, we know it's a weak acid, so minus x won't do anything, so we can just cancel that out, or just remove it. And this gives us 1.2 times 10 power negative 2. So x squared over 0.2 equals to 1.2 times 10 power negative 2. So for x, oh, okay, okay. I didn't acknowledge that the fact that we did actually have the concentration of H plus. We got H plus to be 0.2. So in fact, this is going to be 0.2 plus x. So the equilibrium, the the Ka expression is just going to be 0.2 plus x times x. So x times 0.2 plus x. Now, if we do this on the calculator, I'm doing so many things wrong here. I didn't even put this. My God, guys, please be careful when you solve. Wait, let me just do this properly. Products over reactants. Because I feel like I'm doing something wrong here. Okay, whatever. Um, Here they want us to find the pH, so we got x to be 0.0107, so x is equal to 0.011, I guess. Yeah, if you round it to two decimal places, sorry, to two significant figures, it's gonna be that. So to find concentration of OH plus, we're gonna do 0.2 plus that. So 0.2 plus 0.011 to give 0.211 as a concentration of H. So now you can just do negative log H plus concentration at equilibrium. Negative log answer gives us 0.675, so 0.68. They got, okay, uh, we got a fairly similar answer. They did negative log 0.20. I did negative log 0.211. So I guess they rounded this one to two decimal. They rounded this one to two decimal places, I guess. No, one decimal place. And then they just did negative log. So we got an, an approximation. Okay, yeah, here they approximated this to be 0.2, and then they did that. Okay, I'm just gonna skip straight to question 19, and that should be the end of it. Okay, so, uh, which of the following species is amphoteric? So we know amphoteric is can act as both an acid and a base, right? So acids, we know that they give protons, they're proton donors, so they give H plus, and bases, they're proton acceptors, so they take H plus. So to take H plus, it has to have a negative charge, and to give H plus, it obviously has to have H plus, right? So let's have a look at these ones here. Um, let's just rule out the ones that don't have a negative charge. So this one, and this one. So now let's compare between this and this. CO3 minus, CO3 2 minus does not have so it does not have an H atom. So we can say that C is the answer, and that's correct. So here. Same thing goes for this question. So let's rule out the ones with no negative charge. This, and this. This one doesn't have an H atom, so that goes away. So our answer is C. C and C. Okay, perfect. Um, I'm gonna try to find solutions for these questions later on, but now I have to go somewhere. But I just wanted to get this video out before I left. So yeah, good luck, guys. Hopefully you're benefiting from this, and I'll see if I can do chapter 12 tonight. Bye bye. Take care.